Okay, well, welcome everyone. Thank you for coming, and thank you people online for connecting. We will have today two talks. The first one is by Jorge Padial Doble from Vanderbilt University, and he's going to tell about solar flares with machine learning. So take it away. And then we will have Tsang from Harvard Physics Department. We'll talk about strong lensing, dark perturbers, and machine learning.
All right. So hello, everybody. My name is Jorge. I'm a fifth-year PhD student from Vanderbilt University. I've been working, this project was made with a collaboration between the FISC Vanderbilt Bridge Program, Vanderbilt University, the University of Chicago Computer Science Department. And I'll be talking today about part of my thesis, which is called the ALEXIS Solar Flare Catalog, and how we use machine learning to kind of identify and refine solar flare catalogs. So first, you don't want to do this, okay?
Not working.
All right, I guess I'm gonna have to stand here. All right, so why should you care? So there's a lot of solar transient events that occur on the solar surface that affects life on Earth. Some of these events can cause radio blackouts, can cause disruption to our power connections, and it really depends on the magnitude, right? How strong these solar events are and the time that it has to travel to us, right? Mostly, we're talking today about solar flares, but there are also other things like solar energetic particles and coronal mass ejections, and they take about a couple of hours to days to affect Earth, right? There isn't really a lot of literature on this, but nevertheless, kind of the spectrum of impact that we're talking about is trillions of dollars worth of infrastructure in the next like 10 months when one of these events happens, right? So that has a lot of different considerations. I suggest you go into these publications to read a little bit more. It's very interesting to see how the trade between different countries will be affected by solar flares, right? So it's important to kind of predict when these events are going to happen. So let's talk a little bit about the data for predicting solar flares. The first type of data that we have that we put into these machine learning models are the definition of a solar flare. The standard is we use the XRS signal, which is the X-ray signal, the X-ray flux across the whole solar surface. This is integrated flux. And so the standard definition is that you have 3 monotonically increasing data points, and that defines the start of a flare. You also have the peak of that emission, which would be the flare magnitude, and then you have a slow decline phase, right? But this telescope doesn't have any type of spatial resolution. So the spatial resolution, so where solar flares happen is actually given to another instrument, which is called a solar X-ray imager. And it was built primarily to identify these transient events in the X-rays. It's a multi-pixel image with different filters, different exposures, and it's not really that good of a data set. It hasn't been used basically for publication in the 10 years that it's been available. But the ALEXIS pipeline was able to using computer vision was better to identify the center, and as such the solar radius, the solar border. And now we're able to actually include all of this data into the SunPy program. That is one of our contributions. The other telescope, you guys know about this, is the Solar Dynamics Observatory. They have one of the instruments, the Atmospheric Imaging Assembly, and it takes high resolution, high cadence images across different parts of temperature regime, probing different phenomena, probing different ionizations. And then the other data product that we have is the helioseismic magnetic imager. Here you can see a video of basically the 2 main data products. One of the data products is all these colored regions that you see. These are active regions, they're tracked. And then the boundary boxes across these active regions, they calculate magnetic field features that are associated to enhanced flare activity. And so the machine learning model, then what do we try to do with machine learning is use this time series to try to predict which of these boundary boxes, which of these magnetically unstable regions will produce a flare, right? And the main assumption is that we know when and how strong, and we have a correct solar census, right? But actually mapping from the single pixel to the active region that produced it is actually fairly difficult, and that is kind of where my thesis went forward. We do this in 2 ways. One of the ways is redefining the way that the standard solar flare definition is flagged, What we do is we take that 2-second time series, we fit, we resample, and then we take the derivative. This is what we call the differential analysis of the XRF signal. And here you can see that we flag 2 different regions in the magenta. And we're not saying that these are flares, we're just flagging possible flares, right? It's worth noting that under the standard definition, only 1 flare would have been identified here. So let's talk a little bit about the observational solar flares and why we decided to use the EUV and the X-rays, right? So on the left, what you're seeing is the standard way that we identify solar flares across the whole electromagnetic spectrum. On the x-axis, you have time. On the y-axis is the relative flux. And you can see that the solar flares kind of propagate through the whole electromagnetic spectrum. And they behave differently depending on what part of the ENM we're looking at, right? But what I want to show with this is that basically they have defined certain phases to the solar flare, mostly using the X-rays, such as the impulsive phase, the gradual phase, the impulsive phase, and the decay phase that we talked about earlier, right? On the right, you can see kind of our theoretical description of what is happening during these magnetic reconnection events. And what we basically think is that these are some flux tubes in the magnetic field, magnetic potential energy, and they get intertwined, they release magnetic energy very abruptly. And it has different physical properties that propagate through the whole, what a solar flare is, right? And for the most part, we can see that the EUV and the X-ray kind of probe all of these physical features. It's very difficult to separate these physical features, but we know what is happening, right? Or so we think. So solar flare in the era of HMI, we have really good data, right? This is a 16 megapixel image at every 12 seconds, 7 different wavelengths for AIA. So it gets very big very quickly. And we've been looking for about 13, 14 years, which spans a couple of a solar cycle. And we also, across all of the instruments, we have about 25 petabytes worth of data. The resolution is really good. We have about 0.6 arc second resolution at the solar surface, and you can kind of see it represented here with the Hurricane Maria in Puerto Rico 2017. So the question then becomes, are solar flares predictable and forecastable like hurricanes, or are they unpredictable like lightning, right? So let's talk about how people use ML in this space for solar flare prediction, right? We have 2 eras, the era before HMI, these magnetic field patches that we talked about earlier. We have the era before that, right? Right now we're only concentrating on from 2010 onward. One of the physical features, we already talked about this, is a time series of magnetic field data. We're able to track them across kind of 14 days worth of data, and they probe different parts of the magnetic. All these properties are like related to solar flare activity. There's another time series that is created, which is kind of decaying exponential depending on the active region and how many different types of events have happened. And there's also a census, a running time series of, for this particular active region, how many C class, how many N class, and how many X class flares have you produced. Resolution a lot worse than I thought, but nevertheless, whatever. So what is the setup? The setup is we use this time series and we label each of these elements in this time series as flaring or non-flaring, right? So what we do is we take all of the time series and we say, for an active region, let's label all of the data within a time range of, let's say, for example, 24 hours. All that will be labeled as positive class, and every other part of that data is labeled as a negative class. So this is kind of where, from 2018 onward, this is the supervised setup that we have. And it's a classification task, right? We're trying to classify flare or non-flare. Most of the times, the best producing models try to identify M or X class flare within the next T hours. And the problems with this field is that most of the time, most of the literature doesn't talk about the standardization. How do we normalize that data? They don't really talk about that. They also don't talk about what they do with the missing data, right? So this is another problem in the field. And there's also a weak standard for how do we separate our data into train, test, and validation sets. And so here's a plot that shows 10 years worth of data using different machine learning models and kind of where their standard deviation is in the TSS space, right? So we talked about earlier, true signal score. We talked about setting these classification tags and putting them into different categories, but in practice, it really isn't placing it into categories. It's a continuous value. And this threshold, where we set that threshold, depends what we're going to label as flaring and what we're going to label as non-flaring. And we try to optimize for different metrics. And this example is the true skill score. There are other metrics, but they're underreported in the literature, right? So we should start doing that.
Sorry, could you just define TSS?
TSS, okay. So it's a measure of how generalizable the model is, taking into consideration the true positive, false positives, and all of our true negatives, false negatives. So it's a way of kind of I have the equation in my mind, but nevertheless,
Yeah, no, there's a bunch of different skill scores, and I can't think of them all straight. I just, but anyway, okay, it's
all right. Should have been
That's fine.
prepared for that one. So we try to optimize for the TSS, right? And the other metrics that are important are the area under the curve from a precision recall curve, right? That's another one that's the one that's underreported and the one everybody like nowadays really cares about. So there are a couple of possible reasons why we're stuck here, right? And you say, okay, we're not doing that bad, right? Over here, KNNs, this actually suffers from the standardization problem that we were talking about earlier, and also the train tests. They put all the data, they randomly separate stuff into train tests, but when you're looking at time series data, you're basically, if you do that, you're memorizing. And other ones here in the other section, we have deep learning methods all the way up to a linear model. And the best performing one is actually a linear model, right? So why can't we, with all this data and with all these models, why are we lingering around this region, right? There's some possible reasons. We have reached as far as possible. The data is labeled incorrectly or a combination of above. And for my thesis, we went into the data is labeled incorrectly. We're labeling incorrectly the active regions. That's the main contribution of the thesis, is that ALEXIS is able to map from what the solar flare, when, what, and how strong the solar flare was to the active region that produced it. And we do that by using a convex optimization. Here you see the data that we already know. We have multi-pixel images. We have the single pixel X-ray. And this is the gist of most of the project, right? We run some clustering techniques. And we're able to find one region of interest and take the integrated flux across this region. We're also able to find another region of interest and get the integrated flux around that region. So the question then becomes, can I figure out what weights I need to multiply each of these time series such that when I take the linear combination of it, it produces the X-ray flux, right? So we're producing single pixel emission of the X-ray by using multiple regions in the EUV. So how close can we get to that? And once we do this, we're able to better map from the active region that produced it, from the flare that happened to the active region that produced it.
so this is a great idea. How stable does the EUV to X-ray ratio for each of those as a function of time have to be, so that you're not worried about that?
So I'll show you that they're actually vary. They follow each other fairly well, extremely well, right? Some events where they don't follow each other are in very energetic events. Some of the reason that might be is kind of heating of the plasma and letting that plasma cool down to that emission. You kind of have this time difference between the X-ray peak and the EUV peak. But for smaller flares, it is like straight on.
Okay,
Yeah.
that's great.
This could be, is a completely different scenario, but we cannot measure UV for other stars. We don't have a way to do that, and it's really important for exoplanet atmospheres. Do you think this, if you learn the correlation between the X-rays, and there are some attempts to do that between X-rays and UV, applied to stellar spectra?
So we will see some plots that might be able to answer that question. I think so. A lot of work, but can we constrain what the EUV emission or what the X-ray emission should be from looking at the EUV, or can we constrain from looking at the X-rays down to what the EUV should be? That is something that I'll show you a plot
Okay,
in the next couple of slides.
very useful.
Great. So how does ALEXIS cluster regions of interest, right? We call these candidate regions, and we do this using semi-supervised clustering. It really is unsupervised, but I have a physical meaning for each of my steps, so each of my hyperparameters, so I call it semi-supervised. So basically, let's walk through that real quick. We have different wavelengths. Oh, Jesus, this looks a lot better on my screen. And this is like DPI 300, so I don't know, whatever.
That's fine for back here.
So we have different wavelengths, right? Here we're looking at 131, 193, and 94, I think. And so first we find for each timestamp, we have a bunch of data, right? We have every 12 seconds, we have an image of these. We can find all the peaks. We find all the values that are greater than some threshold that we set, right? And then we want to cluster these peaks, right? There are places that things could be happening. There could be many peaks, when there are also places that there only be one peak, right? And we cluster these in space, right? Are you within a certain region? Let's cluster you, and now you are only one peak, right? We could also make it continuous in time. Solar flares are events that happen not only at one specific timestamp, but they have to happen across a specific time range, right? And so we cluster in time. We need it to be continuous in time, and we also need it to be continuous hyperspectral. So basically, you can think of this as collapsing in that degree, right? We have all the possible spatial clusters. We collapse that in time for each of these wavelengths. We collapse all the wavelengths together, and we're able to get hyperspectral clusters. From these regions, we use a convex optimization to kind of get to our final result, right? In this convex optimization, we use a lasso. Mainly we use a lasso because we want to drive some of those coefficients to zero. So this L1 regularizer allows for that, L2 doesn't, right? And so what we're trying to predict is the target signal. This is the X-ray data, right? This is single pixel XRS data. We also found in this example 2 regions, the yellow region and the blue region, and that will go into a T by N matrix, T being time, N being the number of regions that we found. And so what we want to do is find the weights such that we can multiply each of these regions and recreate that flux as good as possible. That's the beta function here. There's also the lambda, which is the amount of penalty that we give our fit. And that lambda is going to go from 0 all the way to 10, 0 being basically a least squares model.
So sorry, beta is a vector of coefficients.
Yes.
One for each region you
Yes,
found.
so it's
As a function of time.
So each time we're going to have a new beta vector, new beta vector, right? And we'll see a movie of that now.
But then you're tuning lambda so that you drive betas to 0 if you don't really need them, but you want to make sure you kind of have the same number of betas across time, or are you going to I guess you let things come and go.
So through the regularization path, right, this X value, I'm gonna figure out what weights are the best. I'm gonna optimize for some metrics.
I see.
And then if that coefficient goes to 0, then I really don't need you, right? And so there's physical meanings to the coefficients too. I constrain them between 0 and 1. 0, I don't need you. 1, I need your signal, right?
Right.
So, okay.
Sorry, apologies, it's a little bit unclear to me. So what is X here? Is the theory?
So X is a matrix of T, right? So for each data point that we have, and of dimensions T by number of clusters that we have. So it's basically a time series, right? So there are 40 elements in time that we're looking at. And so it would be a 40 by 2. Each member in that row would be the integrated flux at that point from our region, right? So it's just the time series.
And Y, what is Y?
And Y would be the target signal, right? The single pixel X-ray. So we're trying to get the linear combination as close as possible to the single pixel. A dot product between beta and X will give me a 1 by N vector. Go ahead.
What's the time sampling that you use for beta compared to the data?
Excuse me? Sorry.
What's the time sampling that you use for beta compared to the data? I presume it's probably like, it must be sparse somehow, right? Otherwise, it would be like completely arbitrary.
So beta will be at every single point in the regularization path, right? So there's no time cadence in beta. Beta is just the vector that I fit, right? It's a vector of coefficients that I fit. So it doesn't have to do anything with time. Beta has to do with the amount of regularization I give the lambda. So as lambda changes, that beta vector, the way that I optimize for it, will change. Let me see if a video is a little bit more instructive.
So Peter with the coefficients of
the fit. Of a fit. So beta will have, in this example, it's a 1/2 vector, where the first element of that vector,
okay, Peter does not change.
beta does not change with
Yeah.
time. Beta only changes with lambda.
This answer.
Yeah, okay, sorry. All right, awesome. And so there are a couple of metrics which we optimize for. One of those metrics is the Pearson correlation value. The other metrics is the root mean square error between the two vectors. And then two more metrics which take into consideration the system. One of those vectors, one of those metrics measures, it's a minimization function, it's complex optimization of how similar the two vectors are. If the vectors are very similar to each other, that coefficient will be 1. And also the total energy in the system, right? If the total energy in the system is 16, and let me not go that way, we can talk about that later.
Do these different metrics really give different answers? Because it
Excuse
kind
me?
of seem, do these different metrics really give different answers? Because they seem pretty related, so.
So they're related to each other. So they do give different answers. And the way that I made my model later, where I do all the possible combinations, then you kind of always optimize for like the best one, right? First, I did a lasso on all of them, and then I said, you know what, let me do a lasso on all the possible combinations, every single thing. So like 14 million convex fits. And so that kind of got me to, I can show you a plot later on where you kind of see that distribution.
If it works.
It worked. I wasn't expecting it to, but it did, which is pretty cool. Nevertheless, we looked at about 14 terabytes worth of images, right? This is for my proof of concept. So let's look at some examples, right? We already know this data, right? We have the active regions, we have the solar border, we have the EUV, we have the single pixel flux. Let's look at the players in the game. There's Noah. Noah defines solar flare. Everybody goes to Noah first, right? This is their flare duration. This encompasses the gradual, impulsive, and declining phase, right? And that's where they identified it. This is their peak. There's another player in the game, which is Lockheed Martin. Lockheed Martin built the ALEXIS telescope. The metadata is very similar to each other, right? Let's look at what ALEXIS does. We found one region, which their location from the other teams is within my integration box. That's actually like 10 pixels worth of a box. And we can see that the flare happened at some certain time range, which isn't where they identified it, right? So in this example, for this flare, Lockheed Martin and the other teams found it correctly in space, but didn't find it correctly in time. And we could also find another region, right? Where we found another flare completely apart from where the first flare happened. And that one is not in space with the other teams, but yes, in time with the other teams, right? So when we take the linear combination, we're able to reproduce it fairly well. And here goes to the question that you were asking, Cecilia, or if we can constrain it, if we know the X-rays, right? Maybe if we know the light curve, maybe we'll be able, using ALEXIS and the sun as our model first, be able to find what constrains that. And for example, what is the X-ray magnitude for this EUV, right? It is not what it's supposed to be because it's a linear combination, right? So we're overestimating this flux.
But you get the whole flux, you don't get the spectrum.
You don't get the spectrum, right? Yeah.
Well, it's good.
Maybe we could look at that later on. There's EVE data, which is 5 terabytes worth of data for the whole time. And it should be fairly straightforward to kind of go through that, although it's a lot more complicated. Here's another example, synchronous flares. First observational example of synchronous flares happening at the same exact moment. Again, the locations, our integration, the other teams, what they thought about, and we actually find 2 regions. This is another way of constraining. Can we constrain the EUV? Can we map from what the EUV was to what the X-ray should be? We're overestimating, right? And we also have 2 different active regions exploding at the same time. So now 2 active regions go into the positive class, all the other active regions go into the negative class. Previously, only one of them went into the positive class. We're not perfect, right? We still miss a little bit of data. We're able to pick up what region it produced, but we're not able to pick up a peak. And really, we just need more data to be able to complete this. There are other reasons why we fail. I'm more than open to talk about this later. Let's talk about the results. So here, how much time do we have? I can skip this. Done?
Yeah.
Okay, so let's skip this.
We can always talk, so at 1 we have sandwiches and keep people can chat and
That's totally fine. So this is the main results, right? When I compare my catalog, the ALEXIS catalog to the catalog produced by other people. In gray, you see when they either identified it wrong in space or in time, like we talked about. And in teal, you have the ones that I missed. In total, we looked at 1,000 flares, right? This is our proof of concept. And this is the results for that. So we're able to increase the solar flare catalog, the ones that are reported for Earth, which is the X and the M class. And we also missed about 4% of the events. Remember earlier, we were talking about the differential technique, right? Where we're flagging solar flares. This is a plot that shows our peaks to the peaks from other teams. And although we have a lot of peaks, there are false positives here that would have to go through the whole pipeline to actually identify if they were a flare or not. I reported on 1,000 flares found here. Those were the 14 terabytes of data. And we're currently working at Argonne on all 8,000 flares from 2010 to 2020. This encompasses about 100 terabytes worth of images and tens of thousands of node hours. Finally, the ALEXIS data product will be given to the public, where all the plots that you have seen in this presentation, you can create them using that data product. Now, this is important for various parts of solar physics and national security. I'll just leave some here. We can talk about this later. So thank you. I want to give thanks to Kelly Holly Bockelman, who gave me the opportunity to be PhD student. I was actually rejected by 40 graduate programs before she gave me an opportunity. Eric Jonas, who took me in at the University of Chicago, and Christopher Moore for his valuable insight. Thank you.
We interrupted you enough, but if there's a quick question, we do have to move on to the next talk, and then we can always ask more at one. But, yeah, go ahead.
I just have a quick question about how does this compare with those X-ray plus data sets from
So the X-ray flux data from GOES.
Yeah, how does your prediction compare with those in the public?
Could you repeat the question for me?
So the question is, how does my data product compare to the GOES data product? And the GOES data product will be in red here. That's the SWIFC. So SWIFC is not, they're not very good at identifying where it happened, but they are the basis for when it happened, right? So when it happened, it would be over here, right? I'm able to pick up everything that they say in the past 10 years and give more. You could ask what happened up here, right? It's a very small number, but actually, if I were to use the non-science quality data product, after it has been cleaned, I pick them all up, right? So all of these were from non-science quality data products, right? But yeah, we're able to reproduce it, and we're able to do about 63% better in this sample. No worries, thank you. Appreciate it. What? No worries.
Okay, now we have Arthur Tsang, and he's going to talk about strong lensing, dark perturbers, and machine learning.
Thank you.
All right, yes, Ben, thank you for the introduction. Yes, I just wanted to add, I'm a 6th-year PhD student working in Conrad Borkin's lab. So it's at the Jefferson Physics Building, not super far away. All right, so, right, I guess to get started, just for a brief outline of this talk, first I will start with dark matter motivation, then go on to an introduction to strong gravitational lensing, and then we will talk a bit about gravitational perturbers, how we can find them and distinguish between two different types.
We have no video online. Sorry, but we have no video online.
Let's go to display settings.
I mean, I see it online. So.
You see it?
Yeah.
Oh. All right.
Do other people see it online?
No.
Yes, I can
can't see. I have no signal.
I can see the slides.
Okay, so maybe it's one person that cannot see it? Maybe it's switch desktops or something?
Yeah.
Okay, I don't know, but okay, other people see it, must be just the settings.
Yeah. Okay, that is, I don't have to connect to Zoom myself, right?
No, you're,
Okay.
you're also,
Okay, I can see it now. Thank you.
Oh, great, okay. Okay, yes, and then we will go on to how we can use machine learning to make fast detections, and then go on to the conclusions. All right, so, all right. Okay, yeah, so the dark matter motivation is basically the structure of dark matter has been quite well measured at scales that correspond roughly to galaxies and larger. So the cutoff is about the size of the Large Magellan Cloud pictured here, so 10 to the 11 solar masses. Or this corresponds to distance scales between different clusters of about 1 megaparsec. So now the question is, of course, we still don't know what dark matter is, and we want more data about it. And so different dark matter models produce very different predictions at smaller scales, even though they all look the same at the larger scales, because we already have good observations there. So just to illustrate that, here's an example of some ethos simulations compared with CDM. So ethos is a hydrodynamic simulation that includes different models of self-interacting dark matter. And as you can see in all of these simulations, on the large scales, they all look virtually the same, but on the small scales, they look very different, especially with regards to the abundance of the small structure. So we need observations at these scales to distinguish between them, but the structure corresponds to small halos that are very inefficient at star formation. So these are quite dark, especially when they're far away. We cannot observe these directly. All right. So what do we do? So then the strong lensing to the rescue. So the idea is if we can use the lensing effect of these small perturbers, then we might be able to get a handle on these and actually start getting observations on them. So strong lensing as opposed to weak lensing means that when you have light that gets bent by these mass sources, it is deflected enough that you get these Einstein rings or arcs. So this kind of a shape, and the warping is obvious by eye. For weak lensing, on the other hand, what you have is basically you'll get a galaxy, and then there is some overall shear as the light passes towards us, and then in the end there'll be a slight change in the ellipticity, for example, but you would not be able to tell the difference between that and an unlensed galaxy unless you look at many at the same time and you look for correlations in their ellipticities or something like that. With strong lensing, you just need a single system, and you can definitely tell what is happening. In addition, for the strong lenses I'll be talking about, these are usually dominated by one lens, in particular, so there will be one particular lens redshift plane, and usually one source redshift plane as well. And then also this is where convergence that I might use later. The convergence is just this field that's normalized based on the distances, and this corresponds, it's proportional to the 2D mass density. If we project down this lens, so you can think of the convergence like that. It's defined in terms of deflection angles. All right, and so physically there are two kinds of small perturbers that we're interested in. The first kind historically has been studied a bit more. It's called the subhalo, and this basically just corresponds to substructure within a larger structure, which is the main lens. In addition, there's another type that we call the interloper or line of sight halos. And so these are halos of similar size to the subhalo. And these also affect the light, but not within the main lens itself, but as the light is traveling from the source to the main lens or from the main lens to us, the observers. Yeah, from a lensing point of view, they have similar but distinguishable effects. I can go into the difference more later. And physically, another thing to note is that the subhalos are more complicated because they're interacting with the main lens. There's a lot of baryons here, lots of feedback, and there's also an effect called tidal stripping, which is fairly difficult to model. So actually, if we can tell these apart, the interlopers are easier to connect to the actual dark matter models. And so now, with regards to actually finding perturbers from observations, yeah, I think of these in two main classes. The first is individually. So you can use a source agnostic forward model in order to check the multiple different images for consistency. So here you can see this arc at the top and the arc at the bottom. These have to correspond to the same source image. And so you can run a model making some assumptions about how smooth the lens is. It takes about days to weeks in order to run these chains. And then by the end, I'd like to draw your attention to the bottom right here, where you have this image, and then this is the additional convergence or the additional mass density that you would have to add in order to create the best residuals. And you can see that there's a peak around here. So in this paper that they say, all right, we have found a detection of a subhalo over here. All right. So that is good. At the same time, there's another thing you could do, which is to find perturbers statistically. If you look at smaller perturbers, you will not be able to detect their individual effects, but there are many, many more of these. So it is possible to measure their cumulative effect. This is a forecast from a paper from 2016 about how you can use ALMA radio data of a strong lensing system in order to put some constraints. These are fairly large, but still constraints on the power spectrum of the convergence. So this means you can get a handle on about how much structure there is at various scales. All right, and then there's this project that I contributed a little bit to about looking at that same system that I showed 2 slides ago, where now we said, okay, we've been thinking a bit more about these line of sight interlopers, and so we wanted to reanalyze the structure, and so you can see at this plot on the right, this dashed line over here is the redshift of the lens, and on the x-axis are the different redshifts. And we see indeed the PDF of the distribution for the best fits is very much located behind the C lens. So it looks, according to our fits, that the subhalo is indeed actually most likely an interloper. So that was nice because now we're starting to look at real data and analyze it a bit more carefully and get some more clues about how we can connect it to the dark matter models. At the same time, though, there will be a large deluge of data. So today there are on the order of hundreds of strong lensing systems. The illustration here is a catalog of Hubble images of strong lenses. But by 2030, there's expected to be on the order of 100,000 strong lensing systems. And I just read the names of some telescopes, James Webb since 2 years ago, Euclid since last year, then Vera Rubin is expected to come online next year, and then the Extremely Large Telescope in 2028. And so we will need methods that can scale, and so of course this is where the AI comes in. Something else I wanted to note is that with regards to the individual detections, most of the systems that have been studied turn out not to have a detectable perturber. It's only a relatively small fraction that do. So, all right. But first, onto the machine learning architecture. We tried several different things. What turned out to work the best for us was the UNet. So this is a versatile CNN-based architecture made for labeling pixels of an input image. So historically, originally this was introduced for looking at biomedical images and trying to label if any of these pixels correspond to a tumor. But then it was found that this approach works very well in all sorts of different domains. And the interesting thing about this is that it processes information on a range of scales. And so it's called a unit because when you draw the diagram, the information flows in this kind of a U shape. Where as you go down, it shrinks the height and the width by a factor of 2 every time. And so once you're down to this bottom-like layer, it's like an 8x8 compressed image, and this means that we're analyzing on all different scales of this image, but then all of the information has to come back up so that in the end, every pixel has its own label of what kind of classes the machine learning thinks it belongs to. All right, so then of course the question is, how can we use this on strong lenses? And so the first question I tried to tackle was to distinguish between subhalos and interlopers. So the important thing to know here is that you can define a deflection angle field in strong lensing, and you can take a curl of this field. And if there's only one plane of lensing, so that is to say, if everything is the main lens on the subhalo, the curl field should be 0. If there are multiple planes, then there should be a non-zero curl field. And indeed, what we found is that we were able to get the machine learning to produce a discretized version of this curl field. So here's what the true image looks like, and then here is a prediction. So that was all well and good, except that this did not generalize when we added noise. So, this is one of the problems that we frequently encountered when trying to use machine learning. As we try making systems more realistic, things that used to seem like they were working would break down. So then the question is, what can we do keeping lensing systems realistic? So now there's this other problem about just finding individual detections. So there was some earlier work in my lab where they tried finding individual detections, and then it worked until you tried making the sources realistic, and then things would break down. And then so we went through a long circuitous route of trying to adjust the machine learning model and trying to incorporate our knowledge of strong lensing and everything. But then in the end, when we went back to the unit, we found that things were working. We just had to tweak the kinds of subhalos that we were looking for. So as you can see in all of these examples, these are all sets of 3 subplots. Yes.
Sorry, what is the difference between subhalo, between the actually extra perturbers and the noise? Because you associated a curve for those that are not subhalo but extra perturber. But
Yes.
still, I don't know what is the distinction between the two. But I'm just saying that a particular perturber, depending on the mass and geometries and so on, can be also a noise or vice versa, or not, they're different.
Sorry, I think I wasn't clear about this. The noise I'm talking about here it refers to the fact that these images were generated using simulated data, where originally we were using pure noiseless simulations of the lensing. But of course, in order to make these simulations more realistic, you would have to add some amount of noise that corresponds to the amount of noise that you would get when using an actual telescope image. So once we add this noise, then we find that the machine learning is no longer sensitive enough to be able to reproduce this effect.
Right, correct. And then the quick follow-up, what is the difference between subhalo and extra perturber? Because one of them is associated with non-zero curve, I mean the second one.
Yes. Yeah, sorry. So I kind of wanted to go over this really fast, but so the subhalos are always at the same redshift as the main lens, whereas the interlopers are at different redshifts. Yes, and so it is the redshift difference that causes the curls. Yes. Okay, yeah. Sorry, I wasn't clear. Okay. Any other questions? All right, I'll keep going. Right, so then what I'm showing on this slide are sets of 3 subplots. The first one is the original image. Now we have added noise, and importantly, now these sources are not just analytic sources, but they're actually taken from real galaxy catalogs. In particular, we're using the Cosmos galaxies here, and you can see on some of these. The central subplot shows where the subhalo is, and then on the right shows the unit prediction. So on these, for example, it shows the prediction very clearly. It gets it right. On these ones, not so much. And the difference is the mass of the subhalo. So this kind of makes sense. The more massive it is, the stronger the signal, and so the better we're able to reproduce the results. Yes, and so to quantify the accuracy, we made some raw curves. Just to summarize, the false positive is the x-axis and the true positive is the y-axis. So since we want to minimize this and maximize this, we want all the curves to be to the up and to the left. And these different colors correspond to different bins of subhalo masses. For simplicity, for this part, I'm only using subhalos. The line of sight interlopers have a similar effect, but we're only looking at subhalos versus nothing at all right here. All right, so at a roughly Hubble resolution, it works okay. At a medium resolution, it works much better. Still, certainly not perfect. And then if we do an ELT-like resolution, it's about the same as this. So in particular, what we want to point out is that at a very low false positive rate, you were able to predict a fairly large number of these systems with a very high certainty. And then as you try increasing the true positive rate a bit more, then the false positive rate suffers a lot. So this kind of means that you can think of there as being two classes of systems. One in which there's a very clear detection, and then another one in which you see hints of a detection, but it's a lot less clear if there is something or not.
Arthur, is it obvious why things don't get better going from 20 to 10? Is that saying something about the sort of Einstein radius of the perturber or something?
Yeah. So I don't have a good explanation for why this is. I mean, you could imagine that at some resolution it will just start to saturate because the noise on each pixel dominates over the spatial resolution. Something else that we did, which we should have explored a little further, was trying to look into different PSFs. So I think I think the smallest PSF we used was 10 milliarcseconds, but maybe if we had tried using 5, then maybe for this resolution it would have had an additional increase. But yeah, I don't know. Okay.
Sorry.
Yes.
Do you understand why the trend is like that? Why heavier halos see basically, higher actually true positive rate than the lower ones? Because they're like less robust to, like more robust to the actual halo than the noise, right?
Right.
Okay.
Yeah. So basically the amount of the deflection angle due to the perturber is roughly proportional to the mass of the perturber itself. Right. So.
Yeah, but there is also saturation that happens for them that does not happen, for instance, for 10 to the 8.
I think you can just say that the saturation is because it's already doing so much better than the 10 to the 8. So something else about block curves is this diagonal line means that you're doing just as well as random guessing. And so, if you compare how much the height increases compared to random guessing, it also actually is kind of saturated. Yes. Right. The other big thing we found when looking into this is that concentration matters a lot. So in the slide before, what I was showing was a concentration of 60. If we try using a concentration of 15, then now we're doing absolutely terribly. It basically broke the entire system. And so actually, we took the circuitous route, and it's kind of matches what we found before. So just to go to physically what the concentration means. Yes, sorry, it's a bit low, but I'll just say this all in words. C equals 15 matches lambda CDM simulations, and C equals 60 matches recent observations of actual perturbers, roughly speaking. Of course, there's some range in both of those. And the other bullet point says C equals 15 with simpler sources. That is to say, analytic cirrus galaxies. The exact detail is not important. That this works when you have simpler sources. So actually, in my group, there was earlier work in which we just assumed that we should use the lambda CDM simulation concentrations. And in that work, they found that machine learning was working, but only when you had a simple source. So this wasn't very practical. So what we're showing here is actually, it looks like machine learning is a lot more practical than we thought. It's just you have to be careful about what kinds of subhalos are you able to find.
I mean, C60 is also almost a delta function, and this is gonna work well on delta function.
Right.
Yeah,
Yeah, it's much, yeah.
yeah.
Okay, and so now let's let's say it's 2030, and then we have the 100,000 images, and then we have a machine learning model that's good at detecting where there are these gravitational perturbers. Then how do we connect this with the dark matter? That's still a remaining question. So probably the easiest way to do this is to follow up with targeted chains. So using the same kinds of techniques that worked before, but now we know which systems we have to look at, and where to initialize the positions of these subhalos or interlopers. But now there's a particular parameter that we're especially interested in, which is the mass profile slope. So this also this is also highly correlated with the concentration. You can model the mass profile of these perturbers as effectively power law, and you can use the power law slope to distinguish between different dark matter models. So this is the interesting thing, and then Gemma in the back and others have shown that you can actually recover the statistical effect from low mass perturbers using machine learning. And just to illustrate a bit why this power law approximation works. Here's a graph showing a mass profile for an individual perturber, where the x-axis is the distance from the center and the y-axis is the mass density. And you can see that it is not actually a power law, but if you take into account the error bars, then you will see that the error bars are narrow within a fairly small region of distances, and so they call this the region of maximum observability. And so within the region that we're actually sensitive to, you may as well model things like a power law. Yeah. And so this will be kind of the figure of merit that you compare with the dark matter models. Okay, so just to summarize everything, sorry. So if we want to learn more about the nature of dark matter, we want to learn more about the small scale information. So 10 to the 11 solar masses and smaller. The probe that we've been studying with perturbations to strong lensing. And so there are two types: the subhalos within the main lens, and then the line of sight interlopers. And these can be detected either individually or statistically. We're working on making this scalable thanks to machine learning. In particular, we use the units for fast detections, and then these can be followed up with more rigorous, more traditional methods, or possibly with further machine learning notebooks. And these detections are difficult, so we showed that at least for the algorithms that we have tried, we really need to focus on high concentration subhalos. Future directions include modeling with explicit machine learned priors for what a galaxy should look like. Here we were doing this kind of implicitly learning from the training data, but only looking at already lensed images. There was some other work from last year where they found that you can also generate convergence maps and sources directly, but they did not specifically quantify how well this finds substructure, so that should be something interesting for them to look into. Something else is expanding to cluster lenses. So right now, all of my work has been focused on galaxy lenses, but you can have a much larger lens, which is a cluster. And effectively, what this means is that the individual galaxy gets lensed into these different images that are very far away from each other, but of course that are still correlated and that still should be able to be mapped consistently. So this is another possible extension. And then finally, we can also extend machine learning to find other kinds of perturbations, such as an external line of sight shear. When there's no strong lensing, there's a complete degeneracy with the ellipticity. When there's strong lensing, now you have a lot more information to work with. So this is possible. All right. Yeah. Thank you for your attention.
We have a question online.
Oh, okay, go ahead.
Yeah, so you mentioned the importance of concentration, and I just heard the word degeneracy. So I was just thinking, how complex is the parameter space of the perturbers, and therefore, are you worried about degeneracies? How far, ahead are we really? Because you have to train these networks, right? So in order to train them, you have to really understand all the possible parameters for the perturbers.
Yeah, so right now, based on our ability to reconstruct things, there's effectively just two parameters that you can use to model a perturber, and then even the quality of our reconstructions, we cannot do better than that. So you can think of this as either a mass and a concentration, or maybe the power loss slope and its overall amplitude. Right. Yeah, of course, in principle, there's a lot more. This would be a whole set of different bins of mass densities at different distances, but we're not sensitive to that, at least not yet.
Any other quick questions? Or online? Yeah. Almost every time. Yeah, we can always continue discussions over lunch, which I don't know, if we receive this language.
Yeah, there.
Oh, they're there, okay. So let's thank both speakers again.